Hello, chemistry students. Today is an exciting day. We get to combine a lot of the skills that you've been practicing so far into something called stoichiometry. Stoichiometry is the calculation of quantities in chemical reactions. So it's asking if you have a certain amount of reactant, how much product can you produce? Or if you need a certain amount of a product, how much reactant are you going to need? So you have done stoichiometry problems. I'm going to guess you have done these before when you make cookies. So here's our little example from the kitchen, sugar cookies. The question is asking us, how much butter do you need in order to make 24 cookies? When I'm looking at a stoichiometry problem like this, the first thing I do is pick out the important information from the story problem. So it's asking me, how much butter do you need? That's what the answer needs to be. And the information it gives me is that we want to make 24 cookies. Okay, the next thing I do is I make sure my equation is balanced. Here's our chemical formula for sugar cookies, but it is not balanced. So I'm going to go ahead and I'm going to add those coefficients for you. All of this will react together with some heat to form 48 cookies. Okay, so now that my equation is balanced, I'm going to use the railroad track method to calculate how much butter I will need in order to make 24 cookies. So my known value, I start with that on the top left. It's 24 cookies. That's over 1. And now I'm going to use the molar ratio or the coefficients to tell me the ratio between butter and cookies. So for every 48 cookies, I need 1 cup of butter. So that's the ratio I'm going to put in my railroad tracks. The same unit, I need the unit cookies to cancel out, so I'm going to put that one on the bottom. And cups of butter goes on the top. Okay, so now remember, using this method, you multiply everything on the top and everything on the bottom, and then you divide those two values. And you also have to double check your units. So you need to make sure that all of the units that you don't need in your answer cancel out, and you're left with the unit that you want, which is the case right here. So 24 times 1 and 48 times 1. When you divide those, you get 1/2. And then you insert the unit, cup butter. This is the exact same process we're going to be using with stoichiometry going forward. I just wanted to give you this example to show you that you have done this before, but the units you'll be using when we're talking about chemical formulas are just different. These are units that you're used to. And it might seem a little more difficult when we're using units like moles, atoms, grams, but it's really as simple as this process. Okay, and I also want to remind you that in stoichiometry, the number of atoms on the products and reactants side is always the same. The law of conservation of mass states that matter cannot be created or destroyed. Okay, so we're going to work with this example on the next couple of slides. It is the chemical formula to produce ammonia, a gas. So the first thing we're going to have to do with this chemical formula is balance it. So to begin, we have 2 nitrogen, 2 hydrogen, And on the right, we end up with only 1 nitrogen and 3 hydrogen. So let's balance our nitrogens first. If we put a 2 in front of ammonia, we end up with 2 nitrogen and 6 hydrogen. And now we just need to put a 3 in front of hydrogen gas. So that's going to equal 6. Okay, so what you're doing here is you're actually balancing the number of atoms on each side of the equation. So what you have is 2 nitrogen atoms on both sides and 6 hydrogen atoms on both sides. So overall from the reaction, you go from 8 atoms into 8 atoms. Now, this is not always the case for molecules. When you're thinking about molecules, the numbers are not always the same on either side of the reaction arrow. Let's look at the same example, production of ammonia. So you have 1 nitrogen molecule, which consists of 2 atoms, but it's only 1 molecule. You have 3 hydrogen molecules, and you end up producing 2 ammonia molecules. When you're doing this, you end up with 1 times 6.02 times 10 to the 23, or Avogadro's number, molecule of nitrogen plus 3 times 6.02 times 10 to the 23 molecules of hydrogen, and that will form 2 times 6.02 times 10 to the 23 molecules of NH3. The next thing, and maybe one of the most important things to be thinking about, is the number of moles. So remember, a mole is 6.02 times 10 to the 23 atoms, or 6.02 times 10 to the 23 molecules. So this one is pretty easy to think about, actually. You have 1 mole nitrogen plus 3 moles of hydrogen, which form 2 moles of NH3. So overall, in this situation, you're going from 4 moles into 2 moles. And that's okay, because the types of moles are different. You're still following the law of conservation of mass because you have the same number of atoms. Okay? And finally, mass. So remember that you can find the molar mass of any atom from the periodic table. So I'm going to write down the molar mass of the 2 atoms that we're using in this equation. Since these are calculated using grams per mole, we're going to start out with the number of moles. So we have 1, 3, and 2. Let's see. 1 mole times, and this is nitrogen 2. It's N2. So it's not 14 grams per mole. Make sure you multiply that by 2. Each atom has 14 grams per mole. So it's actually 28 grams per mole. And that's for nitrogen. You're going to add that to 3 moles times H2's molecular mass, which is 1 plus 1. That will react to form 2 moles times 17.0 grams per mole. And that is for NH3. Whoops, sorry, and this one is for H2. Alrighty, so let's continue. Simplifying this, we have 28 grams, and that's because you see the moles cancel out. We're left with grams in all of these calculations. So we have 28 grams plus 6 grams yields 17 times 2, which is 34 grams. So in this case, the mass on each side of the reaction arrow is equal. Moles were not equal, but when you bring it back to the mass, it will equal out on both sides because the number of atoms are always the same. And then the atoms weigh the same on both sides. So when you're talking about mass, law of conservation of mass comes back. All right, so let's do some practice, kind of similar to the cookie example, but this is the type of question you'll see on a test or the type of question you'll see from a professor in college, okay? So acetylene gas is produced by adding water to calcium carbide. They give you a balanced equation, which is nice. And the question is, how many grams of acetylene are produced by adding water to 5 grams of calcium carbide? Okay, so that's a lot of information. First step, just like in the cookies, is to identify the important information for solving the stoichiometry problem. First question in pink, what are they asking for? Is how many grams of acetylene are produced. Okay, the information they give you to work with at the beginning is 5.00 grams of calcium carbide. They also give you a complete balanced equation, which is awesome. Okay, so from here, we can skip the balancing step and move straight into our railroad track calculation. Always start with the known value in the top left hand side. All right. So they give you a mass to start with, and they give you the mass of this reactant. They're asking for the mass of this product. Now, you can compare the molar ratios of these two, but first you need to calculate the number of moles that are in 5 grams of calcium carbide. So you can't just put the molar ratios in first. You have to convert it into moles. And you're going to do that, you go from mass to moles, using the molar mass on the periodic table. Okay, so the molar mass of calcium carbide is 64.0 grams per 1 mole. We want the unit grams to cancel out, so we're going to actually put the number 64 on the bottom. And mole on the top. Okay, so now we can use the molar ratio between acetylene gas and calcium carbide, which is a 1-to-1 ratio. So for every 1 mole calcium carbide, we have 1 mole of acetylene produced. Okay, so now we have the right substance as our final unit, but they don't want to know how many moles, they want to know how many grams are produced. So we'll need to add one more step to our calculation. We do this by finding the molar mass of acetylene. And I'll just tell you that it is 26.0 grams. So in this time, we're going to put the unit we want on the top so that the unit currently on the top cancels. So we're going to put 26 on the top this time. Okay, next step is check your dimensional analysis. Make sure all of the units cancel properly. So we've got 1 gram on the top, grams on the bottom, moles of calcium carbide on the top and on the bottom, so those cancel, and then moles of acetylene on the top and moles of acetylene on the bottom. So the only unit that remains is grams of acetylene, which is what they want. So we'll do the math now. Multiply everything on the top and everything on the bottom, and then divide those two values. So we get 130 divided by 64.0. That equals 2.03 grams of C2H2. Okay, let's do one more practice together. The reaction of fluorine with ammonia produces dinitrogen tetrafluoride and hydrogen fluoride. How many grams of dinitrogen tetrafluoride can be produced from 225 grams of fluorine? So let's identify what they're asking. In pink, they want to know how many grams of dinitrogen tetrafluoride can be produced. So they want it in grams, and that is the substance they want to know about. The information they give you to start with is 225 grams of fluorine. Now, luckily, this equation is already balanced for you, so we're going to skip straight on down to our calculation. The information we know is 225 grams of fluorine. Now, just like last time, we are using this balanced equation where we have this reactant and we want to know how much of this product is being produced, but we cannot put that molar ratio into our calculation until we have fluorine in moles. Okay, so right now it's in grams. we'll need to use the molar mass of fluorine from the periodic table to calculate how many moles of fluorine are in 225 grams. So the molar mass of fluorine is 19 grams per mole, and we have a fluorine molecule, so we'll need to multiply that by 2 and put that value on the bottom so it will cancel. Now that we have fluorine in moles, we can use the molar ratio from the balanced equation to convert the problem into dinitrogen tetrafluoride. So for every 5 moles of fluorine gas, you can produce 1 mole of dinitrogen tetrafluoride. And our final step will be to convert dinitrogen tetrafluoride into grams, because that is what the question is asking. Okay, so the molar mass of nitrogen is 14. Dinitrogen tetrafluoride is equal to 104.0 grams per mole. That number is going to go on the top. Okay, so now we multiply everything on the top, do everything on the bottom. We're going to check our dimensional analysis, make sure everything cancels. Okay. My apologies, I should be more specific. Okay, so 23,400 divided by 190. My calculator says 123.157. Don't forget your significant figures during these problems, okay? So the problem gave you 3 significant figures. So that's how many should be in this question. So we have 1, 2, 3. What does 1 do to 3? Nothing. So our final answer is 123 grams of dinitrogen tetrafluoride.